Cody Rue. This is Church of Logic. I'm still with Rob and Chris, and we're still talking about linear logic. And I think we'd gotten to a point where it seemed natural to talk about the computational interpretation of all this linear logic business. Now, we don't have to. We can still. You were talking about the other connectives or the other rules for the connectives. But I do think it's kind of, let's see, I think it's useful to talk about the computational interpretation because A, that's one of the motivations for this whole deal, and B, I don't know, it's fun.
Yep.
All right, so what's the deal? What is the deal with the computation, the computational interpretation? Are we talking, I mean, I had one bit about, logic programming, so deduction as computation. And then I had a bit about Curry-Howard, which is not that, right? It's a different interpretation, and that's more like proofs as programs,
right?
And cut elimination as computation. So which one are we going to talk about now?
I think we were moving more naturally towards the latter, towards the
Curry-Howard
interpretation, because when we're thinking about width like a projection, that's fundamentally thinking about like
elimination forms
forms and projections, right? Like if you've got a tuple and you can say like x dot 1 to get the first element of the tuple and x dot 2 to get this, or e dot 2 to get the second element of the tuple, that is that's a projection. That's the Curry-Howard interpretation of the and elimination or with elimination if you're in linear logic.
Okay, so we have this connective that's like A with B. You can get which one you want, but you can only get one. And you're saying that computationally, getting the first one is like, taking the first of the tuple, and getting the second one is like taking second. Okay, but can we back it up a little bit? I mean, yeah, sure, I can do that in a programming language. That doesn't make this like a linear programming language. So what's different about a linear programming language?
Yeah, well, I mean, I actually kind of first want to say the fact that it doesn't make it a linear programming language is still actually a salient observation, because you could also note that in a lot of standard functional programs, actually projecting isn't the standard way to eliminate pairs. Instead, you do pattern matching. You say, either let or match or something of, some pair of variables, x comma y, equals the thing I expect to be my pair, and then carry on with x and y being the components of the pair. And that elimination form actually corresponds to the tensor elimination in linear logic.
So I think it's worth pausing on this, because people that are familiar with, Java, or I hesitate to say C, but some other language
without pattern matching.
Let's say Java, right?
Yeah.
You don't really have that. This is kind of a cool. I actually really like this, like in Camel or some other ML language.
Or Python. I mean, people come from C and they're like, oh, I can do a destructuring assignment in Python, and that's beautiful.
Okay, great.
JavaScript has destructuring assignments, right? Like this is
so
not
this
actually
is really useful, right? Because you often want to say, hey, I know this thing is a structure. Just give me it all. I want to see inside of it. And then you do an assignment, and on the left hand side of the assignment you say, oh, I want to see it. I want to see patterns for everything, right? So if you have a pair, you do let the x and y equals the pair. Or if you have a record with what are interesting things in a record? Head and tail. That's just kind of sad.
Well, that's a list. That's the
first name, last name.
First name, last name. Great. You say, hey, let first name equals
first name,
some variable.
Name.
I'm going to give it a name. And last name equals y. Let that be my record. And so you get them all at the same time. And again, I'm trying to fit this into my mind space, but this does feel like you're getting everything at once, right? It feels like you're getting both in this one step. Whereas in the other one, you have to call first or you have to call second. And those only give you one at a time.
And so this is actually a really exciting direction because linear logic has forced us now, and we're actually following a historically accurate trajectory in this conversation. Linear logic has forced us to acknowledge that there are two kind of fundamentally different ways of undoing an and, right?
Okay, but let's drill down a little bit. I can get, let x, y equals a pair, and I get them both at once. But I could also just get let x equals first p, in let y equals second p. Okay, and it feels like those are equivalent. So it might be worth taking a beat and saying, hey, aren't those equivalent?
And they are in regular programming languages that are based on persistent
logic.
normal logic, right?
A type system corresponding to persistent logic.
But in linear logic, 100%
those would be
they're different.
Yeah.
And can you tell me what would fail if I wrote that second one?
So if you wrote that second one, you're using, so if you're saying let x equals first of p and let y equals second of p, so you're using p twice.
Great, okay.
And that's
so p is
disallowed.
in your context.
Yeah.
And once you've used it to build something else, it's over,
gone.
it's gone. Great. All right, well that's kind of exciting.
And that does get us to the usual understanding of linear programming languages, I'm using air quotes, where you have, if you just have implication and tensor-like things and you ignore with completely, so we're just going to leave with aside, then you have this relatively simple mantra of, in a linear programming language, you have to use every variable exactly once. So that's and if you're just looking at a tensor and implication lolly perspective, then you basically get that. Use every variable one time.
All right, let's see. I wonder if it's worth digressing now and then say, hey, this sounds a little bit like Rust. Does it have anything to do with Rust? And I suspect the answer is yes, but I'm not an expert in this.
The answer is 100% sort of.
Right.
Rust was originally derived from and tried to be a linear programming language in some of its earlier forms.
Okay.
But I think it's probably misleading when you're talking about Rust's final form to try to say that there's a Curry-Howard correspondence. But yes, certainly
there is an aspect of linearity in Rust's type system, and this most saliently comes through in the context of its notion of pointer ownership, which is every pointer has to have exactly one owner. So if you're passing pointers around, you can't.
Okay, so there's a world in which roughly you can think of owners as propositions in linear logic, and I don't know, pointers usage as deductions, and you sort of say, okay, well, if I can deduce this in some linear logic, then it's going to be some.
Then there's a Rust program that type checks.
To
do that.
Okay, cool. But let's come back to the.
I will say, if you want to follow that down further, you should have Chris back on to talk about session types and that sort of thing. Because there is this whole other paradigm of programming that's being developed that's much closer to a true Curry-Howard correspondence of linear logic for doing Rust-like things.
Yes, and I would like that. Let's brainstorm that offline. Okay, so let's get back to pattern matching, because I think this is cool, and I feel like I read this paper, by... That's it for part 3. Our 4th and last episode on linear logic is coming up next.